The electrical equipment in a plant normally receives power from an electrical distribution system. An electrical distribution system consists of components that bring power into the plant, convert the power to usable voltages, distribute the power throughout the plant, and protect equipment from damage. Since you're likely to work with electrical equipment on a regular basis, you need to understand how the components in an electrical distribution system function. Some of the main components in a plant's electrical distribution system are transformers. Transformers increase or decrease voltage from one electrical circuit to another. By doing so, they enable an electrical distribution system to provide different voltages to different types of equipment. All transformers work on the principle of electromagnetic induction. The application of this principle enables power to be transferred from one circuit to another, even though there's no physical connection between the circuits. The transformers used in electrical distribution systems operate on alternating current, or AC. Alternating current gets its name from the fact that it reverses direction periodically. In fact, it reverses many times per second. It's easier to understand this characteristic if we look at this graph, which shows how AC voltage would look plotted over time. As the graph indicates, AC voltage increases in a positive direction until it reaches its maximum positive value. Then it returns to zero. Increases in a negative direction until it reaches its maximum negative value. Then returns to zero again. In fact, this cycle of increasing and decreasing voltage values repeats many times per second. To see how this happens, we'll use this illustration of an AC circuit that contains a transformer. The transformer is represented by these two coils of wire called windings. The circuit can be divided into two halves or sides. This side is the primary side. It consists of components that handle power coming into the transformer. In this circuit, the primary side includes an AC power supply, which is represented by this symbol, a switch, and one of the transformer coils called the primary winding. The other side of the circuit is called the secondary side. The secondary side components handle power leaving the transformer. In this circuit, the secondary side includes the other coil of the transformer, which is called the secondary winding, and a load, which in this case is an ammeter. The ammeter indicates current flow in amps through the secondary side of the circuit. During operation, the switch is closed to energize the primary side of the circuit. This causes current to flow from the AC power supply through the switch and the primary winding of the transformer and back to the power supply. As current flows through the primary winding, a magnetic field develops around the winding. The magnetic field is represented here by a series of lines called lines of magnetic flux. The nature of the alternating current that passes through the primary winding causes the magnetic field to expand and collapse repeatedly. As the magnetic field expands and collapses, the flux lines cut across the secondary winding. This induces a voltage in the secondary winding and causes current to flow through the secondary side of the circuit. The ammeter detects the current flow, and its pointer provides a visual indication. As we've just seen, alternating current creates an expanding and contracting magnetic field, which induces voltage and enables a transformer to work. Now, the output voltage from a transformer depends on the ratio of the number of turns of wire in the primary winding to the number of turns of wire in the secondary winding. This turns ratio determines whether the transformer increases or decreases voltage and by how much. For example, if there are more turns of wire in the secondary winding than in the primary winding, the output voltage will be higher than the input voltage. In other words, the transformer will increase or step up the voltage. On the other hand, if there are more turns in the primary winding than in the secondary winding, the output voltage will be lower than the input voltage. In this case, the transformer will decrease or step down the voltage. Different kinds of transformers can be used to increase or decrease voltage from one electrical circuit to another. The components that make up these transformers can vary as well. Let's take a look at some basic transformer components now. We'll start with this typical substation transformer. Electricity enters the top of the transformer through power cables. Bushings are used to insulate the cables from the transformer casing. The casing of the transformer provides a housing for the internal parts. Inside the transformer casing are the windings. The windings are usually mounted on an iron core, which concentrates the magnetic field produced in the windings. Besides insulating the windings, the oil also cools the windings, which can produce a lot of heat during normal operation. Some oil-cooled transformers have radiators to make the cooling process more efficient. In the arrangement illustrated here, there's a natural circulation of oil. As the oil picks up heat from the windings, its density decreases, causing it to rise. The warmer oil enters the top of the radiators, where its heat is transferred through the radiators to the surrounding air. As a result, the oil becomes cooler and more dense. The cooler oil sinks to the bottom of the radiators, then re-enters the transformer, where it can pick up more heat from the windings. Some oil-cooled transformers use mechanical devices to aid in cooling. For example, this transformer has a set of fans that move air through the radiators to help transfer the oil's heat to the surrounding air. Transformers can also have oil pumps. They create a forced circulation of oil through the transformer and its radiators. Now, not all transformers use oil to cool their windings. For example, this transformer is air-cooled. It has a set of fans that blow the air that's heated by the windings out of the transformer casing. Screens at the bottom of the transformer let cool air in to replace the heated air. As an operator, you may be responsible for periodically inspecting the transformers at your plant. Inspecting transformers at regular intervals can help in detecting problems before they become serious. An important part of transformer inspections is knowing and following all applicable safety procedures. Safety is an important consideration whenever electrical equipment is involved. Generally, equipment or connections that can cause an electric shock are located out of reach. Equipment or connections that can be reached are often protected by shields or cages. These devices help prevent personnel from coming into contact with energized equipment. Fences are sometimes installed around equipment such as transformers to prevent unauthorized entry. But keep in mind that with or without protective devices, contact with electrical equipment may not be safe. Even low-voltage equipment can cause injuries. And energized transformers often use high enough voltages to cause death if the proper procedures aren't followed. There are a number of general checks that should be made during a transformer inspection. For example, if there are more turns of wire in the secondary winding than in the primary winding, the output voltage will be higher than the input voltage. In other words, the transformer will increase or step up the voltage. On the other hand, if there are more turns in the primary winding than in the secondary winding, the output voltage will be lower than the input voltage. In this case, the transformer will decrease or step down the voltage. During the inspection, if any loose or broken wires are noticed, they should be reported right away. Also, the affected area should be kept clear until the problem has been corrected. The casing of an oil-cooled transformer should be checked for leaks and signs of corrosion that can result in leaks. A good place to check is the joints where piping is connected to the casing. When inspecting the transformer's radiators, remove any paper or debris that might be blocking the radiators and interfering with cooling. Monitoring a transformer's gauges can help you detect potential problems before they get serious. Oil-cooled transformers often have gauges for oil flow, oil temperature, and oil level. Now, if a transformer uses fans to help in cooling, be sure to check them for proper operation as well. Excessive vibration or unusual noise may be a warning sign of a problem with the fans. If you see any abnormal indications, report them. In this topic, we examined the basic operating principles of a transformer. We looked at some major transformer components, and we saw some operator duties associated with transformer inspections. Now try some practice questions related to this material. One type of component that's found throughout a plant's electrical distribution system is a circuit breaker. Circuit breakers serve as protective devices, and they also provide a way to isolate electrical equipment from a source of power. When it functions as a protective device, a circuit breaker helps prevent excessive current from damaging circuits and equipment. A circuit breaker is able to do this because it has electrical contacts that open or trip to interrupt current flow to a circuit. When it functions as an isolating device, a circuit breaker is tripped by personnel to isolate equipment from a source of electric power. This allows equipment to be locked out of service so that it can be worked on safely. Here's one type of circuit breaker that's sometimes used in electrical systems. It has an on-off switch. When the switch is in the on position, the contacts are closed and current flows through them. When the switch is in the off position, the contacts are open and current is unable to flow to the load that the breaker is protecting. When a breaker trips, current won't flow through the circuit until the breaker is reset. That is, until its contacts are closed. To reset this breaker, the switch is first turned to the off position, then to the on position. Not all breakers trip in the same way. Some breakers have internal devices, such as electrical coils, that sense excessive current and open the contacts. Other breakers use separate external devices called relays to do the same thing. Relays sense abnormal circuit conditions and send a signal that trips the breaker. One common type of relay is an overcurrent relay. Overcurrent relays protect equipment from damage caused by excessive current flow. Another type of relay, called an undervoltage relay, protects equipment from damage caused by lower than normal voltages. Motors and other equipment are normally rated for a certain voltage. Too little voltage can cause a dangerous increase in current flow. Circuit breakers and related components are often enclosed in separate housings that are grouped together. The housings are electrically isolated from each other so that the breaker for one circuit can be worked on without affecting the other circuits. The housings also protect personnel from coming into contact with the high voltages inside. If abnormal conditions develop in an electrical circuit, a circuit breaker may trip. Before the breaker is reset, it's important to try to determine the cause of the trip so that any necessary repairs can be made. Resetting a breaker without first checking for the cause of the trip could damage the breaker and other equipment, and it could create unsafe working conditions for personnel. Let's watch as this operator goes through a basic procedure for resetting a tripped circuit breaker. Keep in mind that whenever you're involved in this sort of procedure, you should always follow your company's safety regulations. In this example, the breaker that has tripped is used to protect a motor, but the same general procedure can be applied to other circuits as well. First, the operator checks the motor for obvious signs of damage, such as overheating. He also checks to make sure that there are no obstructions that might prevent the motor's shaft from rotating freely. Then he checks the input power cable for signs of damage that could have caused a short circuit or a ground. Either condition could trip a breaker. After finding no obvious problems with the motor, the operator goes back to the circuit breaker and resets it. Then he returns to the motor and tries to start it. If the breaker trips again, he'll report the trouble. He won't keep trying to restart the motor because that could damage the motor and the breaker. The time delay allows time for the motor to cool before it can be restarted. The procedure that we just saw dealt with the protective function of a circuit breaker, interrupting current flow to protect a load, such as a motor. Another procedure, known as racking out a breaker, can be used to physically lock out a load from its source of power so that de-energized equipment can be worked on safely. Racking out a breaker involves physically disconnecting the breaker from its electrical connections. Let's watch this operator go through a procedure for racking out a breaker. First, he makes sure that he's got the correct breaker. He doesn't want to cut off power to the wrong circuit. Then he opens the breaker's contacts using a local switch. Keep in mind, though, that some breakers are opened from a remote location, such as a control room. For this breaker, the operator reinserts the fuse block upside down. This maintains a physical break in the control circuit so the breaker can't be operated. The off label indicates that even though the block is in place, the circuit is still de-energized. Now the breaker can be physically disconnected. Here, that's done by releasing a latch and sliding the breaker out of its enclosure. An indicator on the side of the enclosure shows when the breaker has been disconnected. Often, the controlling link between a plant's electrical distribution system and individual pieces of electrical equipment is a switch. Basically, a switch is a device that can be opened or closed to start or stop current flow in a circuit. There are a lot of different types of switches in a plant, and they can serve different purposes. For example, these disconnect switches are used to isolate circuits in an electrical distribution system. Other types of switches include limit switches, which help regulate the movement of mechanical equipment, and pressure switches, which respond to changes in pressure by opening or closing an electrical circuit. Switches can also be used to help isolate electrical equipment so that maintenance work can be performed safely. Most control panels contain many switches that can be used to start, stop, and position equipment. Switches can also be located at or near the equipment they're associated with. In order to properly control equipment and processes, operators need to know how to operate a variety of switches. Two types of switches that operators commonly use are push-button switches and rotary switches. Push-button switches can vary in design. For example, when some push-button switches are pushed in, they stay in on their own. Others must be pressed and held as long as the switch is expected to operate. When the push button is released, the circuit is de-energized. Still other push-button switches are simply pressed and released to complete an electrical circuit. Push-button switches can have various features, including lights to indicate whether equipment is on or off, and labels to indicate the push button's functions. As long as the button is held down, the equipment cannot be started up from a remote location. Another type of switch that operators sometimes work with is a rotary switch. Rotary switches are rotated to start, stop, or position equipment. As with push-button switches, rotary switches can vary. With some rotary switches, the switch stays in the position that it's turned to. With others, the switch returns to a certain position after it's turned. For example, the normal position for this switch is in the center. Regardless of how the switch is turned, it always returns to the center when it's released. Some rotary switches require a separate physical movement in addition to the rotation of the switch. For example, this switch must be pushed in and rotated to operate a piece of equipment, and pulled out to stop the equipment. Many rotary switches are designed to prevent accidental operation. For example, this rotary switch has a removable handle. The handle can be taken off when it's important to keep the switch at a particular setting. Inside the transformer casing are the windings. The windings are usually mounted on an iron core, which concentrates the magnetic field produced in the windings. In this topic, we examined the basic operation of a circuit breaker, and we looked at steps involved in resetting and racking out a circuit breaker. We also saw how different types of switches operate. Now try some practice questions on this material. When inspecting the transformer's radiators, remove any paper or debris that might be blocking the radiators and interfering with cooling. One type of component that's found throughout a plant's electrical distribution system is a circuit breaker. Circuit breakers serve as protective devices, and they also provide a way to isolate electrical equipment from a source of power. When it functions as a protective device, a circuit breaker helps prevent excessive current from damaging circuits and equipment. A circuit breaker is able to do this because it has electrical contacts that open or trip to interrupt current flow to a circuit. When it functions as an isolating device, a circuit breaker is tripped by personnel to isolate equipment from a source of electric power. This allows equipment to be locked out of service so that it can be worked on safely. Another procedure, known as racking out a breaker, can be used to physically lock out a load from its source of power so that de-energized equipment can be worked on safely. Racking out a breaker involves physically disconnecting the breaker from its electrical connections. Often, the controlling link between a plant's electrical distribution system and individual pieces of electrical equipment is a switch. Basically, a switch is a device that can be opened or closed to start or stop current flow in a circuit. There are a lot of different types of switches in a plant, and they can serve different purposes. For example, these disconnect switches are used to isolate circuits in an electrical distribution system. Other types of switches include limit switches, which help regulate the movement of mechanical equipment, and pressure switches, which respond to changes in pressure by opening or closing an electrical circuit.